Hello, today we will try to see the sinusoidal driving oscillations on a mass spring system. In the previous lecture we have seen some introduction to the concept of mass and spring, because mass spring system is a general model for several oscillating phenomena. For instance, we have considered the horizontal cases generally, but in the vertical sense, we may have a spring and a mass attached to it. So when you displace the mass from its initial equilibrium position somewhat downward, for instance, then it makes oscillations. And we have written this equation, the equation of motion for such cases, as mx double dot equals minus kx. There was no other force acting on it, as we have assumed. So that we have obtained the equation x double dot plus k over mx equals 0, and the solutions to this kind of differential equations is a sine or a cosine, which is almost the same thing. So x of t turned out to be an amplitude which is found from the initial conditions, and cosine omega 0 t minus a delta in the most general form. This was the equation of motion for such cases. This A was an amplitude found from the initial conditions. For example, if I stretch this object, if I stretch the mass from its initial position by a length A, for example, at time 0, and let it oscillate up and down by some natural frequency, omega 0. Let me emphasize again on this index omega 0, because it is not a general any omega. It is defined by some index 0, which means the natural frequency of the oscillating system, because there will also be an omega today, for instance, when we see the sinusoidal driving forces. There is no driving here. We have a system, for instance, maybe vertical, maybe horizontal. It is not very important right now. So this is the equilibrium position, for instance. If I take it down a bit by an amount A at the beginning, it is the amplitude, it makes oscillations with this amplitude up and down. According to the assumption, there is no resistive force. We neglect all kinds of frictions, air resistance, etc. So this is the function that defines the position of the block at any time t. Omega 0 is the natural frequency. Of course, omega 0 we have seen is the root of this quantity. So omega 0, it turned out that omega 0 was the square root of k over m. So it depends only on the force constant of the spring and the mass you attach. For example, let's have two identical springs having the same K. These are identical springs, but I attach a smaller mass to one and a larger mass to the other. According to this expression, of course, the smaller mass will have a larger frequency. Larger frequency means it makes oscillations faster than the other. So, for example, in the small mass case, I displace it from the equilibrium position by somewhat, it makes oscillations with this omega 0. But in the other case, I have a much larger mass, but the same spring, same force constant K. I displace it again, and it makes a smaller frequency oscillations. So it depends on what your mass is and what your force constant of the spring is. This much we have seen in the first part, in the last lecture. Then what did we see? We assumed also that there is another term here. It is not just this much, but we have added another negative term to this, which is b times x dot. What is b times x dot? X dot is the velocity, because remember that x of t is the position of the... We always talk about this object, whatever mass you attach to the end of the spring. X of t was the position, x dot of t was the velocity, and x double dot of t was the acceleration. Of course, all are in the sinusoidal form, because the derivative of a sine is another sinusoidal function, cosine, and if you differentiate once again, you again get another sinusoidal function, minus sine, etc. So these are the concepts of position, velocity, and acceleration. In the new case, we added a second term to the right hand side. It is also negative because, for example, we assume that it is in a viscous medium. For example, as I will do in one of the examples today, for example, you may have a tank filled with a liquid, for instance, and this object is placed in it. So there is a certain liquid, for instance, oil maybe, water for example, or anything else, or a very dense gas, for instance. In this kind of medium, if you take this object a bit down or a bit up, yeah, it may make oscillations, but it may not make oscillations as well. There are other possibilities, as we have seen in the previous one. What were they? Because depending on how strong the dependence of the force, remember this is the resistive force, if any. Of course, in reality, there is always a kind of resistive force in the medium. It cannot be taken as zero for simplicity, but in some cases, we totally neglect it and just get this equation, which is very simple. But in the real cases, it is not as simple as this. There is necessarily a kind of resistive force acting on the object because of the medium, because of the interaction of the medium with this mass, which is oscillating. So this B is a constant, which is a positive constant. X dot is the velocity. So depending on the velocity of the object, there may act a force on this as well. The greater the velocity, the greater the force. For example, if you try to run in open air, for instance, then because of the air resistance, you get some opposite force backward. So you have some difficulty. If you try to run faster, you feel this force more and more. But the slower you are, the less will be this resistive force. If there is no velocity, if you are at rest, of course there is no such x dot, there is no such velocity, no force term. However, assume now there is a bx dot term. So we take it to the left and we obtain an expression of, after dividing by m, etc. We obtain x double dot plus b over m, x dot plus k over m, x, which is 0 on the right hand side. And then we continued by defining a parameter beta, damping parameter, that was defined as b over 2m, not 1m but 2m, but b over m, this part is just 2 beta, so instead of this we substituted 2 beta, and then we obtained a differential equation again. This was a second order, linear because there is no square. This is replaced by omega 0 square. Omega 0 square is not a square term because it is a constant. But x dot, x double dot are not square, they are linear. So it's a second order, linear, a constant coefficient, one a constant, another constant, and homogeneous. Homogeneous means you have a 0 on the right hand side. But today, as I will try to show now, we will have some term on the right hand side, not 0 but a positive term on the right hand side, which is time dependent. It is sinusoidally varying. Now let's consider the previous lecture a bit more in more detail. Then we obtained an equation and we suggested a possible solution. It was an exponential. Possible solution candidate was an exponential. Of course, this R was unknown. Forget about the amplitude. It can be taken as 1 for simplicity. Anyway, it can be found from the initial conditions, where how much you displace from the equilibrium position. And then R is found. How? We write this equation in a manner something times R squared plus something times R plus something is equal to 0, and we have found the roots using the previous expression that we have already known from quadratic equations: a times R squared, b times R, and c minus b plus or minus, this b is not that big by the way, b squared minus 4ac divided by 2a, etc. And then we obtain three possibilities depending on what we have inside this. Is it greater than 0, equal to 0, or less than 0? And according to these different results, we obtain different functions for the solution. Still, we didn't have any, now we don't have still any sinusoidal driving force. This is just a short summary of the last lecture. And then we obtain some possibilities. I will not repeat them. Underdamping, critical damping, and overdamping cases. And let me just draw the picture graph to remember. This was just x of t, and this is the function time t. In the underdamped case, we had a sinusoid, but the magnitude is getting less and less. This is underdamping. It is making oscillations, so the system is making oscillations. For example, this one, this system is making oscillations up and down. However, the oscillations will cease in a moment and it will stop because of some resistive term. This is a possibility. But there are two other possibilities. For example, if you put this system in a very viscous medium such as oil, water, etc., in a liquid, then and you stretch it to some position with respect to the equilibrium, this much for instance, if you stretch it this much and leave it, it doesn't generally make oscillations. If you just come back to the equilibrium case in a manner, in maybe critically damped manner or overdamped manner, because the critically damped case is the following. This is the behavior. It doesn't make oscillation, it doesn't pass to the other side of the horizontal axis. However, it reaches equilibrium in the shortest time. This is first one was that. Second one is critically damped, critically underdamping, critical damping, and last possibility is a case which is called overdamping, and it takes more time with respect to the critical one. So, for instance, this may be the overdamping case. So much we have seen and solved some examples. Now today we will try to see the driving oscillation. What is driving oscillation? For example, we have a mass spring system. We attach a mass to the spring, and then of course if you just displace the object from the equilibrium position somewhat, it makes oscillations up and down for some time, and then it will stop. On the other hand, now we have a driving force applied to the other end. So on the one hand it makes oscillation, on the other hand I apply a certain sinusoidal force up and down, for example, at a different frequency, omega. But the natural frequency of the system, which was root k over m, remember that, omega 0 was root k over m. It was the coefficient of this last term, root of this last term. Now we have an omega, which is the omega frequency of the oscillations, applied on the system externally to the other end. So, for example, I try to apply a force maybe with a very little frequency, very slowly, very rarely. It takes just a few oscillations per minute maybe. Or a very large frequency, and we will see how this object, how this system behaves as a result of our sinusoidal oscillations applied externally. So we will now have two frequencies, omega 0 and omega. Please try to see the difference and don't write them in place of the other. Now in this part we have a mathematical analysis. It takes some time, but I will try to go through slowly and in steps. Now we have sinusoidal driving oscillations. In the previous case, we had x double dot plus 2 beta x dot plus omega 0 squared x is equal to 0. The right hand side was 0. It is a homogeneous differential equation because we have a 0 on the right hand side after this block. Now we will have, for instance, this case. On the other hand, this makes oscillations, of course, up and down with a frequency omega 0, but also we will apply a certain f0, let's say cosine omega t minus delta. This is the externally applied force. Externally applied force. So on the right hand side we will have this term. It will be, for simplicity, let it be an exponential, a sinusoid cosine function with a frequency omega. Let me indicate also that this is omega, not omega 0, of course. And we will see what happens if this is omega 0, for example. With an unknown or known amplitude f0, because we talk about the force. So the right hand side now, x double dot, I write the same left hand side, 2 beta x dot plus omega 0 squared x. On the right hand side we don't have a 0, but we have this function f0 cosine omega t minus an unknown phase factor delta. Or maybe known factor, but we will try to find now. We will try to find a possible solution. X particular of t. What is particular? In general, if you have something other than 0 on the right hand side of the differential equation, the general solution x, let me call it g of t, is the sum of two terms, two functions. It is the sum of two functions. What are they? X complementary, the complementary solution x c of t, and the particular solution which is peculiar to the right hand side, whatever you have given, and the particular solution x particular of t. So we mean the following: x general is the sum of x complementary of t and x particular of t. This is for the case where we have 0 on the right hand side. It was this only previously, there was no particular function, so this was it, this was all. But now, in addition to the natural oscillations of the system up and down or back and forth, we add an external term because we also try to apply a force to the other end of the spring. So there will be necessarily another solution. This is for the particular solution, whatever we have on the right hand side. So this is, for example, in our case, this is for the case where we have f0 cosine something, or an exponential, or a decreasing exponential, positive or negative. A function on the right hand side other than 0. If you have 0, we have only complementary solution. If you have something other than 0, you necessarily have the first one. In addition to that, you have the second, x particular, but we do not know what it will be for such a sinusoidal externally applied force. Now we will find x particular of t in this analysis. We look at the right hand side. Since the applied driving force is a sinusoid, cosine means a sinusoid, is a sinusoid of frequency omega, not omega 0, any frequency omega, we try a function, we try a function in this form. We try a function in this form. It will be a sinusoid, it will be it will have a frequency omega. We try a function in the same form. Same form means it will be a sinusoid also. In the same form with the same frequency. With the same frequency omega. But with a phase factor, unknown factor, delta, for instance. So we have, what do we have now? Let me just write the first line, mx double dot plus b times x dot plus kx is equal to f0 cosine omega t. Assume there is no phase given to this, cosine omega t. Now we divide through by m as we did. So we have x double dot plus b over m x dot k over m x f0 over m cosine omega t. And again, let me substitute as before 2 beta for this term, omega 0 squared for the other term. So that x double dot plus 2 beta for the first coefficient, omega 0 squared for the second coefficient, and on the right hand side, let's say f0 over m, let it be capital A. Capital A cosine, and let's also write it this way, where A is just f0 over m. Our trial function will be what? X particular of t will have an unknown amplitude d, which we will find. It will be a cosine, the same omega t, but with an unknown phase factor delta, where d and delta are unknown, but we will find them. So let us find dn, let us calculate dn delta. Now we will try to find what this d and what this delta should be, because we assume that this omega has to be the same as the applied omega. And we will also try to see the possibility of omega being, for example, equal to the natural frequency omega 0 of the system. Now let our trial function be applied, substituted to this case, xp, here, there, and there. Now let me rewrite xp, x particular of t. For simplicity, I will drop the t dependence, but now let me still keep it. D cosine omega t minus delta. This is our assumed trial function. Then, of course, xp dot of the first time derivative will be, it will be minus sine from the cosine term, minus d omega, omega coming from the inside, sine omega t minus delta. Of course, accordingly, xp double dot, the acceleration of t, will be again minus sine d omega, but there is one more omega coming from the inside, omega squared, it becomes cosine omega t minus delta. So, substituting them in equation 1, let me call it equation 1. Substituting them, these, in equation 1, what do we get? I will drop the t dependence for simplicity and write the xp dot, xp double dot in the correct places. So let me rewrite equation 1 using this trial function. xp double dot. So we have first minus d omega squared cosine omega t minus delta plus b over m, but b over m is now 2 beta, so this is the equation you will apply, 2 beta, 2 beta x dot, but x dot is now xp dot. So we have a minus sign, it becomes minus 2 beta d omega sine omega t minus delta. Third one is omega 0 squared times xp, which is just the uppermost case, d cosine omega t minus delta. On the right we have the applied function a cos omega t, which is external oscillation, a cosine omega t. So this is the new form of equation 1. But we still, of course, don't know what d and delta should be. Now we will apply some simple trigonometric identities. From trigonometry, we know that sine, for instance, a plus or minus b is sine a cosine b, again plus or minus cosine a sine b. If you have the addition or subtraction of two angles, we apply the right hand side. For the cosine case, because we need these cases in our equation to open these terms, we need them. Cosine a plus or minus b will be cosine a cosine b, but in the reverse order, minus plus sine a sine b. So these are the trigonometric identities we will use. So we will open these cosine or sine functions using these identities. Let me go line by line. Minus d omega squared. Open the parentheses. Now we have cosine a minus b. But cosine a minus b is just cos a cos b plus sine a sine b. A and b are omega t and delta. So this is our A, this is our B. We have A minus B. According to this identity, we have cosine omega t, cosine of the other one, delta. We have minus, so we write plus, sine omega t, sine delta. First line. So we have written this. Next, minus 2 beta d omega multiplied by, this time we have sine A minus, because sine A minus t is sine A cos b, again minus cos A cos b. Say cos A sine b. So we have sine of the first, cosine of the next, cosine delta. We have a subtraction, so we write a subtraction. Cos A sine b, cos omega t, sine delta. We have written second line as well. Third line we have a plus omega 0 squared times a d times a d. Again we open this cosine just like the first line. Cosine A, cosine B, cosine omega t, just like the first parenthesis, cosine delta, negative, positive, so we have positive sine omega t, sine delta, sine omega t, sine delta. On the right hand side we have a cosine omega t. Where do we want to go from this rounded expression? Now our purpose is the following. Now our purpose is to write this, let me call it equation 2. Our purpose is to write equation 2 in the form cosine omega t times something plus sine omega t times something else is equal to 0 form. If we manage to write this expression in a simple way, cos omega t times its coefficients plus sine omega times its coefficients equal to 0. Then, since cosine omega t, sine omega t are changing functions, they sometimes become 0, but in most of the time they are not 0. So if this equation has to be satisfied equal to 0, then it needs coefficients to be 0. Okay? So this coefficient should be 0, that coefficient should be 0, and then we will arrive at the unknowns, capital D and delta. So let's try to write this in this form. Alright. Now let's collect the terms multiplied by cosine omega t. So let me just write cosine omega t first. Cosine omega t multiplied by what? Let's go slowly from the first line. From the first line we have minus d omega squared cos delta. Minus d omega squared cosine delta. There is no other. Here we have a cosine term here. Cos omega t term, it is plus 2 beta d omega, 2 beta d omega sine delta. Next, we have a cosine omega t here, plus omega 0 squared d cosine delta. And we have an a coming from the other side, minus a, all multiplied by cos omega t. So we finish this part and continue with the sine. Plus sine omega t multiplied by the rest. What is the rest? Again, start from the beginning. Minus d omega squared sine delta d omega squared sine that. So we finished the first one. There's a sine omega t here, minus 2 beta d omega, minus 2 beta d omega cos delta. Cos delta. We have another sign here. Plus omega 0 squared d plus omega 0 squared d and sine delta. This is equal to 0. So we have, after cos omega t and sine omega t, a block and another block. These blocks are these two blocks in these square brackets. So we will set them to 0. From the second block, let's begin with the second block first. Beginning from the second block is just this part. Let me write them total. Minus d omega squared sine delta minus 2 beta d omega cosine delta plus omega 0 squared d sine delta are all equal to 0. So from this line we cannot find any information for capital D because we capital D is cancelled. There is a capital D in every term. Now we will try to find delta from this, and then going back to the first block we will find what the capital D should be. What do we get here? We have two terms for sine delta, one term for cosine delta. So that sine delta multiplied by, for instance, multiplied by omega 0 squared minus omega squared, and on the right hand side we have, this is passing by as a positive term, 2 beta omega cosine delta. So it is easy to find the tangent delta divided by cosine. So that tangent delta, if you divide it by cos delta through, then we have 2 beta omega divided by omega 0 squared minus omega squared. So this is the first information we obtain for the phase factor delta. It's a tangent. Tangent delta is obtained, so delta is the tangent inverse on the right hand side. But what do we get from here? Let's try to draw a triangle, right triangle, so we understand what the sine delta and cos delta should also be. Now this reminds us a right triangle. So let me draw a right triangle, and this angle let it be delta. So tangent delta, if tangent delta is the right hand side, it means the numerator is the opposite side, denominator is the adjacent side. So we have a 2 beta omega. By the way, don't confuse omega and omega 0, please. They are different things, necessarily different things. 2 beta omega for the opposite side and omega 0 squared minus omega squared for the adjacent side. So what about the hypotenuse? It is the, from Pythagorean rule, we can easily find the hypotenuse. It is the square root of this. There are several squares. Omega 0 squared minus omega squared, together it is squared, plus the square of this, which is 4 beta squared omega squared. So we can easily get sine and cosine delta. For instance, sine delta is 2 beta omega over the root. For simplicity, I will not write the full square root, just write the root, not the inside. Sine delta is 2 beta omega divided by the root. Let me show the root by this red square root, which means what is it inside. And of course, cosine delta is omega 0 squared minus omega squared over the hypotenuse, which is this square root. Now pass to the upper block. Now, considering the first block. First block is the coefficient coefficient of cosine omega t term. So let me write the full parentheses minus d. Start with the first. Minus d omega squared and cosine delta. But what is cosine delta? Let me just replace cosine delta by this parentheses. Well, cosine delta is simply this thing, omega 0 squared minus omega squared over the root. Plus 2 beta d omega plus 2 beta d omega sine delta. But sine delta is from this triangle 2 beta omega over the root. And we continue. Plus omega 0 squared, omega 0 squared, capital D cosine delta, which is this term, omega 0 squared minus omega squared over the root, and finally minus a is equal to 0. And then what do we get here? We don't have cancellation of d everywhere because there is a term which doesn't have d. So we can go to find d. Now find d. If you leave aside d multiplied by negative this thing plus minus omega squared from the first, minus omega squared, omega 0 squared minus omega squared over the root. First term, plus 2 beta omega, plus 2 beta omega, another 2 beta omega by the root, plus omega 0 squared, and this same parentheses, omega 0 squared minus omega squared over the root. Let's take a to the other side, equal to a. So we have some similar terms because this is the root of what is in the numerator. So we have, let's say, d multiplied by. If you consider these as a separate term, omega 0 squared minus omega squared, and the other one plus 2 beta omega squared divided by the root of the same thing. Let me write down the full root, square root. We have omega 0 squared minus omega squared squared plus 2 beta omega squared. Altogether, this will be a. But we have, like for instance, d times, for instance, m over root n type of thing. So these are the same terms. Therefore, this cancels and makes it root n in the numerator. So this becomes, for instance, d multiplied by the root of this whole thing. Omega 0 squared minus omega squared to the square plus, let me take it, open it, 4 beta squared omega squared equal to a. So totally, let me write d a over root of this whole thing. So we obtain the amplitude capital D of the solution to the particular function. So x particular of t is this whole thing. A is f0 over m, let me take it back. f0 over m was capital A, divided by this whole root, multiplied by cosine omega t minus delta. But delta is tangent inverse. Let me write it as delta, where delta is tangent inverse of 2 beta omega over the omega 0 squared minus omega squared. So this is the particular solution. So let's finally state that this is just the particular solution. There is also, of course, the complementary one. So totally, x of t consists of x complementary of t and x particular of t. So if you write the full result, it is the following. Let me write it here. X of t, or x general of t, is on the one hand e to the minus beta t, again e to the maybe real exponential, maybe imaginary exponential, depending on the case. We don't know whether it is an overdamping or critically damping or underdamping case. So we have, this is the envelope, negative exponential, and an unknown coefficient a1, e to the maybe root of beta squared minus omega 0 squared times t, plus a2 e to the negative of this minus beta squared over omega 0 squared times t. This is the complementary part, where we have 0 on the right hand side. But if there is also some external force that tries to oscillate it at a different frequency omega other than the natural frequency omega 0, then we have this part plus this whole thing, f0 over m. f0 is the applied magnitude divided by this root omega 0 squared minus omega squared to the power of 2 plus 4 beta squared omega 0 squared, omega squared, and then multiplied by cosine omega t minus delta, where delta is tangent inverse of this thing. So this is the full result. Total solution is this one. Of course, if there is no applied force externally, this part f0 will be 0, and it is enough for f0 to be 0, but then this whole thing drops. We have only the homogeneous part, complementary solution. If in addition to that, let me repeat the case, for instance, we have this object. If I keep my hand at rest, the upper part of the spring is at rest, then these are the oscillations, up and down. It makes several oscillations until it stops, omega 0. Of course, if we have an underdamped case, we don't have a periodic motion. It is not possible to talk about a period because periods are changing. We don't have the same period during the whole motion because motion stops after a few oscillations. But this is omega 0 anyway. However, if I also move this upper part from the external part by some other omega, maybe in a mild manner, maybe very harshly, this omega may be greater than, even much greater than the natural frequency. So what happens in those cases? And let's try to see the case of resonance. Now, resonance is a very important concept in physics, not only mechanically but also electrically, because in electricity we have just a parallel situation. Again, we have this kind of sinusoidal oscillations. Instead of a mass spring system, we will have, for instance, LC, inductor and capacitor. If the resistance is negligible in the circuit, for instance, in an electrical circuit, in an so there is a very strong parallelism between electricity and mechanics in this case in the oscillations. In an electrical circuit such as LC, so we have an inductor and a capacitor. So we have an L and a C. Then we may have, for instance, a sinusoidal battery or a potential source. Let me write it, for instance, V is equal to some V0 sine omega t type of thing, for instance. Or we just have just a battery, just a constant magnitude battery, for instance. And assume that the resistance is negligible. We have an LC circuit. Then in an LC circuit, of course, we write a similar differential equation. If you apply the Kirchhoff's voltage law to this circuit and traverse once around, you start from point A and turn back to point A, for example, we have potential drops, plus or minus, plus and minus. Maybe we have a sinusoidal source, maybe we have just a battery, for example. Then we apply Kirchhoff's voltage law, we will have, for instance, VL plus VC is equal to V. V is the battery. But in reality, of course, there should be some resistance, so that at least the resistance of the wires that join, that connect these elements should be taken into account to have a better result. In those cases, we will also have a R. For example, we may also add an R to this. So it's an RLC circuit. An RLC circuit is almost the same as what we have here. If you have no other source, no source applied, and just some initial potential, initial charge across the place of the capacitor, for instance, then we have a homogeneous case. On the right hand side, there is no external source. But also, if you have some source, just like this these external oscillations, if you have a source like this, then we will have this kind of solutions. One for the complementary solution, which is for the homogeneous part on the right hand side, if you have zero, no source. If on the other hand, we have a source, a sinusoidal potential source, for instance, which is sinusoidally changing potential, then we have these elements R, L, and C. And in those cases, what is VR, for instance? VR, we also have some V sub R is equal to some V. V is the potential source. Alright, then what is VL? We have L di by dt, as you remember from electricity. L di by dt is the potential drop across an inductor. For the resistance, we have I times R or R times I. And for the capacitor, we have Q over C. That's equal to, let's say, V, for instance. This V may be a constant or a sinusoidally changing one. But we also have I is equal to dq by dt. Let me write it as q dot, just like we do it as x dot in the mechanical cases. So in this equation, if you write all of them in terms of q, I, di, etc., in terms of q, we have, for instance, I is equal to q dot. Then di by dt, which is the first term, will be, let's say, q double dot. So we have L times q double dot plus R times I, which is q dot, and q over C. That's equal to maybe 0, maybe an external source, V. Divided by L, so this term can be equated to 1, then q double dot plus some R over L, q dot plus q over LC is equal to, or 1 over LC times q is better. 1 over LC times Q is just, let's say, V over L. So this term, this equation is corresponding to the case of x double dot plus, what was here? V over M times x dot plus omega 0 squared times x is equal to right hand side, let's say, for instance, maybe 0, maybe F0 over m and a certain cosine function. So this coefficient, these are 1 and 1. Alright, this part is corresponding to this. What was this? 2 beta, which is the resistor term. Here we have omega 0 squared, which is k over m in the mechanical case, corresponds to 1 over LC. So if you have just an LC system, one inductor, a solenoid, and a capacitor only, initially capacitor is charged somewhat, then they make oscillations. Charge is going from one element to the other, and then coming back to the other. It makes oscillations back and forth. So this kind of oscillations in the LC circuit, inductor and capacitor circuit, is just almost the same as the potential and kinetic energy term, for instance, in the mass spring system. And the right hand sides are also corresponding. So the same idea that we have been analyzing here can be applied to the electrical cases of RC circuit, LC circuit, RLC circuit. If there is no R, remember that R here, B there, they are also corresponding terms. So this system, for instance, this system, which is making oscillations, soon stops because of some kind of resistive force, maybe friction, maybe air resistance, etc. But if you assume ideal conditions, then it makes oscillations up and down, undamped, no damping, undamped system. In that case, this will be 0. And we have only these two terms, it is just a sinusoid, back and forth. In this case, if you have no system, no resistive force, this will be 0. In the electrical case, if you have no resistance, just an inductor and a capacitor. Initially, it has some charge, let's say Q0 for instance, then this Q0 goes back and forth, there is a current and vice versa, etc. It makes oscillations. Clockwise, counterclockwise currents will be flowing at the frequency in this case will be 1 over root LC. For example, if you try to tune a radio, if you want to find a certain station, you want to listen to a certain radio, a channel, then you change your system, your radio, you change the frequency so that when it matches with that radio's frequency, when omega is omega 0, in that case you can listen to that station quite well. But if you change this omega a little bit, then it can match with another radio station, for instance. This is the same idea. But we don't go into the details of electrical analysis. Let me consider the resonance. What is resonance? If the system, any system, shows either no resistance or very little resistance to your external steps, external trials, then your external functions, whichever you like, then you may have resonance. For example, for someone who likes chocolate, okay? For example, I like chocolate very much, for instance. Then I don't show much resistance to someone who offers me some pieces of chocolate. For the first one, I can accept. If you offer the second one, I can accept too. If you offer the third piece, for instance, I can also accept the third one. Okay, so I don't show much resistance. Maybe at the end of some nth piece, I can say, oh, all right, it's enough. But for some other food, for instance, that I do not like, for example, I don't give a name for that. If you offer the first piece to me, maybe just at the beginning I can say no thanks, because I have a large resistance for that object. But for some other object, I show no resistance, maybe very little resistance. For instance, let's consider a mechanical system now. Let's say we have a very long rope. Let's say this L is, for instance, 50 meters. And at the end of it, this is the ground. At the end of this long rope, we have a bulb. It's a pendulum. Let's say, for instance, 2,000 kilograms. But this rope is strong enough to hold it. Okay? And we are here. It's a very 2,000 kilograms, but you are here. You are here. If you want to move this very heavy ball at the end of a long rope of 50 meters, for instance, then it is almost impossible. If you try to push this to one side by applying a large force, you possibly fail. So maybe a few people here all together try to push it. Even for those people, it is not easy. However, there is a possibility of putting this system in oscillations. What is that? You can find omega 0, the natural frequency of this system. It is just root k over m for the mass spring system, but for this case we have root L over G, for example, omega root G over L, I think, right? This is the omega 0. G, because we have the, remember we have seen the simple pendulum, and G theta was the term, so something multiplied by theta double dot plus something multiplied by theta was 0. Theta was the angle measured this way from the vertical, and this was a negative term because theta is increasing counterclockwise, but this term is trying to restore it, so it is a negative theta dependence. We take it to S, so this is 1, and that is G over L. L is the length, G is the gravitational acceleration. So omega 0 is just root G over L. G is, let's say, for instance, 10 in SI, and let it be, for example, 40 meters, okay? Let's make it not 50, but 40 meters. So 1 over 4. 1 over 2. Omega 0 is 1/2 radians per second. Omega 0. Now I assume that the pendulum is at rest. Very heavy ball, but at rest. And you want to push it and make it oscillate. If you just tip this ball with your finger, very little impulse, but you don't do this at any time interval. If you do this at any time interval, for example, other than this period, for example, if you apply it, let's say, 1 radian per second. So you just try to tip this object, right? This is the, for example, very long rope and very heavy ball. It is at rest, and you try to tip this object, very little impulses. But then what happens if you do it at any omega, ordinary omega, nothing happens. It is impossible to move this object to sides. Okay? But if your omega is the same as omega 0, which is the natural frequency of the system, then sooner or later, maybe it takes some time, of course, but after maybe a few minutes, it starts to oscillate back and forth. This long rope with a very heavy bulb at the end starts to make oscillations sideways. The key word here is the equality matching of the frequencies. Your omega and the natural frequency of the system, if they match, then soon you get oscillations. For example, this omega, if it is equal to 1/2 radian per second, you can convert it to nu, for instance. What is the relationship? Omega, remember, is 2 pi times nu. Nu is the linear back and forth oscillations, that frequency in terms of hertz. 1 over second, but omega is the angular frequency of radians per second. If you match your frequency of application of tipping just little by little, matches with the natural frequency of the system, then you manage to move this object sideways, and even if you continue to do that, after a few minutes, the amplitudes will get larger and larger. So the resonance may sometimes be a good thing to activate some very difficult systems, for instance. But in some cases, it may cause some harms. For instance, remember the Tacoma Bridge? Remember the Tacoma Bridge, which fell down because of some wind power. But wind, unfortunately, acted on the bridge in an unwanted manner, so that the system started to get resonance, and then it just broke. You can find some videos on the Tacoma Bridge, for instance. All right, what do we want to have now? We obtained D, the amplitude, is A over some root, and of course, X particular of T was this D, which is A over something, A over this root, times cosine omega T minus delta, and delta was a tangent inverse of a fraction, etc. Now our purpose is to maximize D. Now we want to maximize capital D by just playing with external frequency omega. By just playing with omega. So what is the other name for this? It is the maximization of amplitude. What is that? If you take del D by del omega, and omega is equal to omega resonance, let me call it omega r, then this derivative should be equal to 0. Remember, we always set the derivatives of the quantities that we want to maximize or minimize with respect to the variable we can change, which is the external omega. Omega 0 is a constant. We cannot change omega 0. It is fixed to the length and the mass. Not the mass. In this case, it is obtained by the gravitational acceleration and only the length of the rod. Even mass doesn't enter. In the mass spring system, it is k over m. Alright, now you want to maximize the amplitude, because this the amplitude is, remembered, is the amplitude of the particular solution as a result of the applied function. So it is not difficult to take this into account, to take this integral, not integral, in this derivation. Del D by del omega. It is del by del omega of what? A. What was A? It was just F over F0 over M. Not important. But in the denominator we had root omega 0 squared minus omega squared to the power of 2 plus 4 beta squared omega squared. Okay? And this derivative should later be equated to 0. It is a ratio, remember. So del by del omega of some f over g, for instance, f over g. Remember that this is f prime g minus g prime f divided by something which is not important. That has to be 0 to take the derivative. F is the numerator, g is the denominator. So f is a constant, so it has no derivative. So let's start with the first term. F prime is 0, alright, minus f. What is that? Not important, but let me write f0 over m. But the derivative of the denominator. First of all, we have
a 1/2 from the power. 1/2 times this parenthesis to minus 1/2. And this is not important also, because the rest, next term should be set to 0. Multiplied by what? Multiplied by the derivative of the inside. What is that? We have a 2 omega 0 squared minus omega squared multiplied by minus 2 omega from the inside plus derivative of the second part, 2 times 4, 8 beta squared omega will be 0. This is not important. It's a term which doesn't enter into the derivation, but this part should be set to 0. How do we get from here? Let's just have some cancellations, maybe omegas cancel. Let me rewrite it. Take this negative term to the other side, so we have 8 beta squared omega. On the other side we have 2 times 2, 4 omega times the parentheses, omega 0 squared minus omega squared. So there are some cancellations. These omegas will cancel, 4's will cancel. So we obtain 2 beta squared will be omega 0 squared minus omega squared. So we finally get the result. Omega, so this omega is now omega r. Let me write it as omega resonance frequency. It is square root of omega 0 squared minus twice beta squared. So this is the resonant frequency. Let's check for the undamped case. Undamped, for example, is that long rope string at the end of which there's a heavy bob, 40 meters length rope or string or wire, and at the end we have a maybe 2,000 kilogram bob. Assume there's no beta. Remember, there is no resistive force, we neglect them. Then this term drops, so omega 0 goes up as omega 0. Then omega resonance will be the same as omega 0. So it means, again, we come back to the previous statement. If you just tip this little bar, even if you don't look at it, if you just tip this heavy ball with your finger, but at just the right frequency, whatever omega 0 is, you should tip with those intervals, maybe 1 second, maybe 2 seconds, whatever. If you do that, soon you will observe that the whole system will start to oscillate back and forth. If there is some kind of resistance, as we have in the, remember the system where we have x double dot plus 2 beta x dot plus omega 0 square x is equal to the type. If we have such a resistant term, then whatever this beta is, you will write here, multiply by 2, and then find the resonance frequency. If you put them in order, you have 3 frequencies, for instance. Omega 0 under damping, omega 1, omega 0 no damping, undamped case, omega 0 is the frequency for undamped case. Omega 1 under damping, and omega resonance is resonant frequency. And omega 0 was just omega 0. Omega 1 was, remember, omega 1 was omega 0 squared minus beta squared, and omega r is now root omega 0 squared minus twice beta squared. So if you put them in increasing order, for instance, or decreasing order, greatest one is omega 0, next one is omega 1 for the underdamped case, and next comes omega resonant. Now in this part, let's solve some examples so that we get used to the topic better. example, let's have a rod placed on top of a table, but let two springs be attached to its end. So this is B, length of the rod, M is the mass, and K is the force constant of the spring. A rod of mass M, length B, is placed on a frictionless table, and the two ends are attached to springs of force constant K. Find the A, the frequency, omega 0, and B, the period T, of the oscillations. So it is just placed on a horizontal surface, frictionless plane, and two ends are attached to springs like this. So this is the top view of the system. So you look down the table and see this rod. So it can make oscillations around the midpoint of, with some frequency omega 0. Of course, then it has a certain period t. And assume that, for instance, we displace it in the clockwise sense, so that this becomes, for instance, this becomes like that. So that this part, because of the restoring force of the spring, it will be pulled back down, not down, but in this way. Similarly, this will be elongated, the two springs will be elongated, so they will apply restoring forces, so that it will make oscillations in that around the midpoint O. So let's have the formula for the mass spring systems. For instance, we have F equals Kx, but for the rotational cases, like this one, we have tau is equal to, for instance, I alpha type of equation. Okay? Instead of F equals ma, we have tau equals I times alpha. But alpha, we know, is theta double dot. It is the second time derivative of the angle. What is the angle? So this is small angle, this small angle is theta. And torque is, remember, it is the cross product of R and F. It is defined by this. What is R in this case? When you write this, draw this rod like that one. So there is a force because of the elongated left hand spring, and there is a force because of the elongated right hand spring. And that distance is almost half of the length, B over 2 and B over 2. So that R is simply B over 2. F is, now it is almost K times X. But there are two such terms because they both work in the same sense of rotation. So we have to add the two, or we multiply by 2 because they are identical. So total torque is twice B over 2, K and X. But what is X? Remember that for the circular sectors like this, if that part is angle theta, that arc length is X and that radius is, in this case, B over 2. So X is just the product of B over 2 and angle theta. Of course, don't forget that theta to take in radians, not in degrees. So X is B over 2 theta. We put this X here and then we obtain the torque. Torque is these two will cancel. So we have V times force constant K times X, but X is B over 2 and theta. Therefore, torque is K times B squared over 2 and angle theta. But from the equation, torque is equal to I times alpha, and I is for a rod rotating around the midpoint. We know that I, center of mass, I0 will be 1 over 12 mass times length squared. We know this from previous courses. So that torque equals that, and we should unite these pieces of information. So this torque will be I times alpha, but alpha is theta double dot. And of course, don't forget to put a minus sign in this case because of the direction of motion or sense of motion. Therefore, we have on the one hand K times B squared over 2 theta. On the other hand, with a negative sign, I times alpha. I is that 1 over 12 and B squared and theta double dot. So if you write them in the correct order, so we have 1 over 12 mb squared multiplied by theta double dot. You take it to the other side as a positive term. So we have K times B squared over 2 theta. That's equal to 0. Here's a square. So this is like, for instance, in the previous linear cases, like mx double dot plus kx is equal to 0 type of thing. So we want to get the first coefficient to be 1, so we divide by this term. So these 2's will cancel, etc. B squares will cancel. So these B squares will cancel. If you multiply by 2, this will be 6, this will cancel, etc. So that we have theta double dot plus we have after cancellation of B squares K 6 will be here. So multiply by 2, there will be a 6 here. Also an m there. 6k over m, theta is equal to 0. And when you get such an equation in this form, when you make this first coefficient 1, and we have something here in the form of k over m, this, remember, is the square of our natural frequency, omega 0. So that whatever we see here, 6k over m, is just the square of the natural frequency. So we understand that omega 0 is root 6k over the mass. This is the natural frequency in part A. Part B is just the period, remember, is 1 over nu. Nu is linear frequency, but omega and nu are related by, instead of nu we can write omega over 2 pi, so 2 pi goes up. Therefore, period t will be 2 pi divided by this term, and finally period turns out to be 2 pi root of mass of the rod divided by 6 times the force constant of each of these springs. Next example is again we have but this time we have single spring but 2 masses. Two blocks of masses M1 and M2 are attached K, and the system is placed on a frictionless table. The unstretched length of the spring is L. When the spring is compressed from the two ends by an amount, let's say B, for instance, when the spring is compressed from the ends by an amount B, and released, what will be the frequency of oscillations? A, let it be part A. What will be the frequency omega of oscillations? And part B, what will be the equation of motion? Equation of motion. So first of all, we should understand the problem correctly. Let me draw two following instances. So for example, in the first case, we have this picture. So first block, spring, second block. Later on, it is compressed. So this length, first of all, this length is given as F. It is not important, but given. Masses are not the same, different. But now, let's say this part, this left hand is compressed to the right, but that one is also compressed to the right, so that the spring is compressed as a whole. And we understand that the center of mass of the system does not change. Why? Because there is no horizontal force applied on the system. So wherever it is, the position of the center of mass should be the same during the whole motion. What will do the bodies at the two ends? Of course, this will make oscillations like this, and that will make oscillations like that around the initial sort of position. So this part, just this part, is the length. What is that length? Initial unstretched length minus this amount of B in the beginning, but at any time, t, this is just initial length minus x. The position of the center of mass does not change because of having no force in the horizontal sense externally. Does not change. So we should choose a reference position. Let that reference position be, for instance, here. Let it be x equals 0. Then the position of mass m1, the position of m1 is 1. So these are the forces on the two objects. If you consider the length of the spring, what do we get? We have the difference x2 minus x1. So this distance is x2 minus x1. So on the one hand we have x2 minus x1, on the other hand we have L minus x. L is the initial unstretched length, x is the amount of compression, total compression. On the other hand, for the coordinates, we can write x1 and x2. So only this part is x2 minus x1. But this x2 minus x1 is also equal to initial length minus the amount of compression. So this is an equation we can write. So let's continue. Take x on the other side. X is L plus x1 minus x2. But we should get the double dots, second time derivatives. So we differentiate once x dot will be, this will be 0 because L was a constant. It has no time derivative. The other ones are x1 dot minus x2 dot. We differentiate once more, so it becomes x double dot, x1 double dot minus x2 double dot. So let's rewrite this equation by the help of these two. So x double dot. We have x1 double, but x1 double dot can be found here as minus f over m1. Minus f over m1. Minus the other one, but the other one is plus f over m2, but we still have a minus sign, f over m2. So take minus f to the other side as a common multiplier. We have 1 over m1 plus 1 over m2. In other words, we have x double dot minus f m1 plus m2 divided by m1 m2. But what is f? F in general, f is equal to k times x, because this x now represents the total amount of compression. So instead of f, we can write kx. Therefore, x double dot is equal to minus kx times this term, m1 plus m2, sum of the masses by the product. Take it to the left-hand side. Now we have the equation of a mass spring system. X double dot plus m1 plus m2 divided by m1 m2 multiplied by x is equal to 0. And we immediately recognize that this term, with a k of course, don't forget this k, together, this term corresponds to our natural frequency squared. So we understand that omega 0 is root of m1 plus m2 divided by m1 m2 multiplied by force constant of the spring. So this is the frequency in part A. For example, let's make a comment. For instance, if m1 is equal to 1 kilogram, let's give numbers, m2 is equal to 2 kilograms, and for instance k, the force constant, let it be for instance 24 newtons per meter. What happens to omega 0? Then omega 0 is simply sum of the masses 1 plus 2 divided by the product 1 times 2 multiplied by 24, all in the square root. So 3 over 2, it is 3 over 2, 24. So this is just 36. Therefore, omega turns out to be, for instance, 6 radians per second, as a numerical example. Now part B is the equations of motion. Part B, you can easily write equations. For instance, x of t is just initial amount of compression, and the problem was telling us that it was compressed by B. So B was the initial amount of compression multiplied by cosine omega 0 t. What is omega 0? It is this right hand side. Root m1 plus m2 divided by m1 m2 multiplied by k times t, omega 0 t. So this is the equation of motion. Now there is another comment we have to make here. If you look at this quantity in the reverse order, m1, m2 divided by m1 plus m2, the quantity m1 m2 divided by m1 plus m2, in other words, product over sum, not in this way, but product over sum, it is defined as mu. This mu is not the coefficient of friction, it is called reduced mass. The quantity product over sum of the masses without k is equal to mu, which is called the reduced mass. So sometimes it makes it easier to calculate this type of things, because, for instance, we have now, let's say, we have a spring and two masses attached to the ends. And we also maybe elongate it and let it oscillate as it does. So it makes such oscillations. But because the masses are different, for instance, M1 will have larger amplitude oscillations, but M2 will have, because it is a heavier object, for instance, 1 to 2 kilograms, so that this will make this kind of oscillation, this should make a bit larger or vice versa oscillations. However, we can convert it to a new case where we have a single spring, the same spring, attached to it a single mass. That single mass, if it had a value of m1, m2 or m1 plus m2, we would necessarily get the same frequency. So this system is making oscillations with a certain omega 0. That omega 0 is what we have found here, this thing. But we can immediately understand that this is the same as, it is also the same as, okay, a spring and the same force constant K, just like this one. But we have a certain mass here. This mass is called reduced mass. So we have identical oscillations, the same frequency, the same period. We have here two different masses attached to the ends of the spring, and they were making oscillations back and forth with different amplitudes. But if you choose the same mass, they will make same amplitude oscillations. However, same or different, doesn't matter. You can convert it to a new system where you have the same frequency again, omega 0, but this time we have the same spring, but one end of the spring is fixed to the wall, for instance, and the other one is attached to a mass we call reduced mass, but it has a value of this much, product of the previous masses divided by the sum. So this is also important in other areas of physics. We will come back to this when we consider some celestial topics. Let's have another example from damped motion. This time we have a tank full of some liquid, maybe water, maybe oil, maybe some other fluid, or some dense gas maybe. So this is the top, that's the vertical line, and we have now a pendulum. So this pendulum is like that. At the end of a very light rod, for instance, very light rod of length L, we have a mass M. A ball of mass capital M is attached. Now for this system submerged in fluid, we will try to solve the equation. First, let's find write the equation first from the beginning. So net force is what? This is the object, that angle is theta, but what are the forces on it? Of course, this is the mg, weight of the object, but remember that that was mg sine theta, because this is also theta, sine theta, and also there is a resistive term, this given by this right hand side. So both are negative. Net force is, on the one hand, minus mg sine theta. Why do we have a minus term? Because theta is increasing in the counterclockwise sense for such cases, because this is the direction of increase for the angle. However, this is in this opposite sense. So we have a minus sign. But for the resistive force, we also have a minus sign, because it is a resistive force. It tries to slow it down. So another minus sign. This time, whatever we have given, we are given here, twice mass root g times L. L is the length of the rod, g is the gravitational acceleration, and also theta dot. But for small angles, 30 degrees is still in the small angle interval. So this sine theta can be approximated as theta, so that net force here minus mg theta minus 2m root g over L and theta dot. So the equation will be mass times, remember x double dot, but x is, remember, again x is equal to length L times theta, so x dot is L times theta dot, x double dot is L times theta double dot, so we have mass times L theta double dot. If you take the two negative signs, the forces to the left hand side, they are both positive, plus this term twice m root g times L theta dot, and plus the other one m times g times theta is equal to 0. If you divide through by m times L, so that this term becomes 1, theta double dot plus, so altogether we can cancel one of the m's. Divide by L. When you divide by L, we have here, put it in the denominator, we have g over L here, theta dot plus again g over L times theta is equal to 0. So remember that this term corresponds to 2 beta, remember from the first part of the analysis, 2 beta, this part corresponds to omega 0 squared. Now let's continue with this last case. So if 2 beta is this much, then 1 beta corresponds to that. So beta is, we read from the equation, that these twos are neglected. Beta part is just the rest, root g over L. Beta corresponds to root g over L, and omega 0 squared corresponds to just g over L. And remember that when we do this analysis to see whether it is under damping or critically damping or over damping, we have for the roots minus beta plus or minus beta squared minus omega 0 squared divided by 2, etc. No, after cancellation by 2. This is the form of the root. Okay. Plus 1, minus 1. But what about this inside of the root? But if you take these, square of that, beta squared will be g over L. Omega squared is also g over L. So inside the root we have just a 0. And whenever we have a 0 inside the root, we understand that it is the critically damped case. Since beta squared is equal to omega 0 squared, we see that it is a critically damped motion. Critically damped motion. What is the significance of critically damped motion? It doesn't make oscillations back and forth. It just slows down, it falls down, it just falls down, this system, simple pendulum, in the fluid, just falls and reaches the vertical position once. It doesn't go to the other part, because it is the critically damped motion. Remember the graph, critically damped case was this behavior. T is the time axis, x is the vertical axis. It doesn't pass to the other side because there's no oscillation. Alright? But we also derived the form of the solution. What was the form? X of t was an unknown, initially from the initial conditions it can be found, a plus bt times e to the minus beta t. You don't have to derive it again, we have already did it. So we understand that this has to be the solution, but we don't know A and beta. We know beta, but A and B are unknown. They will be found from the initial conditions. The initial conditions are first angle at the beginning, angle at time 0, and speed at time 0, which is 0. Okay. Of course, we don't have an x here. In this case, we have an equation for the angle, not the position, but the angle. So this angle theta will be given by a function. So what is that? Theta of t will be an unknown plus another unknown times t and e to the minus beta t. But beta is found. It is root g over L times t. But what about A and B? However, we have two initial conditions. Theta of 0 is 30 degrees. Of course, we don't write 30 degrees. We write it as pi over 6 first of all. It has to be given in terms of radians. So pi over 6 will be, rewrite the equation. A is unknown, plus b times 0, so we don't have any information about b. E to the 0. E to the 0 is 1, so we understand that A, first constant, should be pi over 6. This is found. What about b? From the velocity we can find the other term. What is the initial velocity? Theta dot of 0 is given to be 0. It starts from rest. So that, let's take the derivative of this first line, theta dot of t. Derivative of the first part, which is just b multiplied by the rest, e to the minus something, plus first term together, a plus bt, and the derivative of the second part, which we have a minus beta coming from the exponent, and e to the minus beta t again. However, when time 0, theta dot of 0 will be, we have a b times e to the 0, which is 1, plus a plus 0 minus beta times 1. B is now found, so the other part is 0. So b is easily calculated. It is a over, a times minus beta. So we understand that b has to be pi over 6 also, but multiplied by beta. What is beta? Root g over F. Finally, theta of t will be a pi over 6 plus b negative pi over 6 multiplied by root g over L times t, there's a t dependence, multiplied by e to the minus root g over L t. Let me write it in a better way and also write the velocity. So take pi over 6 outside. Theta of t will be pi over 6 multiplied by 1 minus root g over L times t. T is outside the root. Multiplied by e to the minus root g over L. Outside we have a t. So at the beginning when time is 0, this term drops. This term is 1. So theta is pi over 6. When you take the derivative, as we did here, you get 0. So this is the formula for the position. For the velocity, for the angular velocity, theta dot of t, we have theta dot. We will take the derivative. Theta dot will be, first we have a pi over 6 coming from the first term, multiplied by derivative of the inside minus root g over L. Multiplied by the second one, g over L and t, plus first one, 1 minus whatever we see here, g over L times t, multiplied by the exponent minus g over L and also e to the minus g over L t. So there is another cancellation here. Finally, theta dot will be, let's keep pi over 6. Also, let's write the explanation because it is everywhere. E to the minus root g over L times t. Multiplied by, from the first term we have a minus 1. We have just root g over L. So we have written this part, that part, remaining part is the middle one. Minus root g over L. Continue. Here we have plus another g over L so from the first one we have that part. From the second part again 1 here, this one multiplied by that, we have a minus sign, minus g over L. And we multiply the next one, it is plus g over L, all multiplied. So they cancel. There's a cancellation here. Let me do it here. So theta dot of t. First of all, we write this pi over 6 multiplied by. Again, we can also take this exponential also outside. It is everywhere. Pi over 6 e to the minus root g over ft. Multiplied by. From the first one, you get minus g over f. So the first one is finished. Next one, plus a 1. But this one means minus root g over L and plus this part g over L without the root. So the theta dot of t, maybe you can get it as twice. So theta dot is found by this result. Now let's have one more example comparing the frequencies of the undamped and underdamped cases. The amplitude of an underdamped damping harmonic oscillator, or when a harmonic oscillator that executes under damped motion, drops to e to the minus 1 of its initial value after 4 cycles. Find the relationship between the frequencies of the underdamped case and the undamped case, undamped oscillator. So what does it tell us here? We have a mass spring system, for instance. It is executing underdamped motion. What is underdamped motion? Remember that it begins from a certain amplitude, makes a cycle, another cycle, another cycle, etc. After the first, second, third, and fourth, the initial value, for instance, this was the initial value, initial amplitude. After 4 cycles, let's say here, it drops to, if this is, for example, x of 0, it drops to e to the minus 1 times x of 0. So this much is, let's say, 37% roughly of the initial case. So this piece of information is given, and we will continue to find the relationship between frequency of the undamped oscillator is omega 0. Frequency of the underdamped case is omega 1. Of course, it is not, as I said before, it is not perfectly valid to say that this is a frequency. Omega 1 is not a perfect frequency because as you look at the underdamped case, these lengths, for instance, this part, that part, this part, that part are not of the same length. These pieces get shorter and shorter, so that it is not a perfectly periodic motion. However, we define some, remember the formula, omega 1 was defined as omega 0 squared minus beta squared. If you compare the two frequencies. However, how do you get beta from this information? X of, let's say, 4 cycles. X of, let's say, 14 will be e to the minus, first of all, we have a term e to the minus beta t. Whatever we have here, let me call 4t, 4 periods, it is e to the minus beta times the same, 4t, and a cosine term, cosine of something, omega 1t, etc. But at the beginning, x of 0 was e to the 0 and the same cosine term. So we are not interested in the changes, so cosines are not important. The amplitudes, the first terms are important. If you divide them, a value at a later time divided by the value at the beginning is e to the minus 1, as given by the problem. So cancel these cosines, they cancel, and e to the 0 is 1, so that e to the minus beta times 4 period is equal to e to the minus 1. So that, take the ln's of both sides for instance, get rid of the exponentials, plus, make them plus, etc. So we understand that from this we get beta times 4t or 4 beta t is just 1. So that beta can be written as 1 over 4t. 1 over 4t. This is a piece of information that we can apply here from the problem. Also, T is equal to 2 pi over omega 1. Now look at the expression here. Omega 1 is root omega 0 squared minus beta squared. But beta can be written as 1 over 40. And beta is 1 over 40. But t can be written as 2 pi over omega 1. 1 over 4 times 2 pi over omega 1. So take omega 1 to the upper part in the numerator, omega 1 over 8 pi. So that put beta as omega 1 squared over 8 pi squared there. So that this equation becomes omega 1 is equal to root omega 0 squared minus beta squared. But beta is now replaced by this last expression. Omega 1 over 8 pi squared. So that omega 1 will be root omega 0 squared minus omega 1 squared over 64 pi squared. So take the squares of both sides. Take the squares of both sides. We have omega 1 squared is equal to omega 0 squared minus omega 1 squared over 64 pi squared. So that take this term to the left. Omega 1 squared 1 plus 1 over 64 pi squared will be omega 0 squared. So omega 1 squared is 64 pi squared plus 1 divided by 64 pi squared is equal to omega 0 squared. Now you take the roots of both sides again and you obtain the expression here. Let me just write it here. So omega 1 is omega 0 times 8 pi divided by root 64 pi squared plus 1. So this is the expression we are after. Alright. So today we saw some examples from various parts of harmonic motion.